When we talk about the clean energy transition, we usually picture the spectacular hardware.
Right.
Huge offshore wind farms, vast solar arrays stretching out across the desert.
It's a very high-level view. And while we celebrate those sources, the sun, the wind, we rarely discuss the foundational material that makes it all possible.
That's exactly what we're getting into in this deep dive. Our sources are, well, they're unanimous. The material acting as a critical enabler, the literal backbone of these modern power systems, is aluminium.
And our mission today is really to show you why this common metal is suddenly so indispensable for building the grid of tomorrow.
And we're not just talking about simple metal sheets. The real innovation is in what the sources call advanced aluminium extrusion profiles.
Yes, that's key. The ability to customize its shape to create these incredibly efficient structures. We're going to analyze how its unique properties are being engineered into, well, every part of the energy supply chain.
Okay, let's unpack this with the basics then. If we're building a new grid, what gives aluminium the edge over, say, steel or especially copper?
It's this compelling combination of advantages. We've been calling it the triple threat.
The triple threat. I like that. What's number one?
First is its unique ratio of being incredibly lightweight, while at the same time maintaining remarkable strength.
That sounds simple, but I imagine when you scale it up to the size of a wind turbine, that weight has enormous consequences.
It absolutely does. I mean, just think about the construction logistics.
Right.
Less weight means faster installation, lower shipping costs, easier handling on site. But the big thing is structural.
How so?
It allows for designs that need less foundation. They put less stress on towers and support systems. And this is where those custom extrusion profiles you mentioned come in.
Can you explain that process a little? For someone who isn't a material engineer, what is an extrusion profile?
Think of it like squeezing toothpaste from a tube, but with heated metal. You push hot aluminium through a shaped die to create a continuous, complex shape. So instead of a heavy, solid block, you can design a profile that is hollow where it can be, which saves weight, but reinforced exactly where you need the strength.
So it's perfectly balancing strength with material efficiency.
Precisely.
Okay, that makes sense. So that's property one. What's number two of the triple threat? You mentioned copper earlier.
Right, conductivity. And what's fascinating here are the cost and weight dynamics.
Because copper is the standard, isn't it?
It is, per volume, a better conductor, but it's also much heavier and far more expensive. For moving massive amounts of power over long distances, aluminium offers a hugely cost-effective and reliable solution.
So we see it in transmission lines, control panels.
Exactly, and in crucial internal components called bus bars. It just gives you the performance you need without the prohibitive weight or the price tag of copper.
So it's not a sacrifice in performance, it's about optimizing performance per dollar.
And performance per kilogram, which is essential if you want to scale this up globally.
Okay, so that's two. What's the third property?
The third one ties everything back to the main goal of the industry, sustainability. Our research shows aluminium is 100% recyclable without any loss of its properties.
That's huge.
It's central to the whole idea of clean energy. And here's the stat you need to remember. Recycling it requires only 5% of the energy needed for its primary production.
Wait, just 5%? That's staggering.
It is.
When you think about the scale of this global build-out, thousands of tons of metal, that fact alone must fundamentally change the long-term carbon equation for the whole sector.
It creates a true circular life cycle. So when today's renewable infrastructure reaches the end of its life in a few decades, the material itself contributes almost nothing to the carbon footprint of its replacement.
That's real long-term thinking.
It is.
Okay, so let's shift from the material science to the actual hardware. How does this triple threat show up in a solar farm or a wind farm?
In solar, it's basically the entire skeletal system.
The frames, the racks.
Exactly. Its lightweight strength and, really critically, its corrosion resistance make it ideal for all the support structures.
Which have to survive in the elements for decades.
Right. From seaside salt spray to desert heat, it ensures that long-lasting stability. But it's doing more than just holding the panels up.
Okay.
It's also used extensively in the components that manage the power, things like inverter housings, cable management solutions.
And for wind power?
Well, the sources mention that by reducing the system weight, it directly impacts the design of the rotating components and the nacelle.
The big box on top of the tower.
Right. It allows for bigger, more efficient, and more scalable turbine designs.
So let's move from generation to transmission. The source material calls aluminum conductors the backbone of modern power networks. Why did it basically dethrone copper for this?
It's mostly about the physics of long-distance transmission. Copper is just too heavy.
So the towers would have to be stronger, closer together.
Yes, exactly. With aluminum conductors, the transmission towers can be lighter, less numerous, and placed further apart. It reduces construction costs significantly.
And that's a huge optimization, not a sacrifice.
It is. You get an excellent conductivity to weight ratio, and you're minimizing energy loss over those long distances.
And minimizing that loss is one of the biggest challenges for any grid, right? We can't afford to lose precious electrons just shipping them down the line.
That's the core challenge. Aluminum helps create conductors that reduce resistance, which makes the whole grid more resilient.
But the grid isn't just wires. What about inside the substations? You mentioned bus bars and lugs earlier. What are those?
A bus bar is essentially a thick, rigid metal bar. It looks like a plank, and it conducts massive currents inside a control panel.
Okay, and lugs.
Lugs are the heavy-duty connectors that attach cables to those bus bars. They're critical interfaces.
And aluminum is used for both.
Yes, and extruded aluminum profiles are perfect for them because they offer excellent electrical conductivity and superior heat dissipation.
Why is the heat dissipation so important there?
Well, high currents generate intense heat, especially in a compact space like a substation.
Right, that makes sense.
And too much heat causes resistance, which means energy loss. More critically, it can lead to component failure, even catastrophic overheating. Aluminum basically acts like a built-in cooling system for these parts.
That's a perfect lead-in to energy storage. Storage is what bridges the gap between when the sun is shining and when we all need power at night. So what is aluminum's role in batteries?
It's a huge role, and it's mostly because of those same thermal properties we just discussed.
Heat dissipation.
Exactly. In any large-scale battery system, you have hundreds of cells generating a ton of heat when they charge and discharge.
Yeah.
So aluminum's the preferred material for the battery enclosures, the casings.
So why is managing that temperature so critical for a battery?
Because a battery's lifespan and its safety are directly tied to temperature stability. The high thermal conductivity of aluminum lets you build very efficient cooling systems right into the battery's architecture. It prevents thermal runaway, keeps it efficient, and most importantly, it significantly extends the battery's life.
So if you want a battery system to last for 10 or 20 years?
You need aluminum managing the heat.
So it's not just a box to hold the cells, it's an active management tool.
Absolutely. And to do that, those extruded profiles we talked about are manufactured into heat sinks.
Those finned metal things you see inside electronics.
Right. They're complex components that manage the thermal load of the batteries, the inverters, everything. They are integral to the whole system's efficiency.
So it's structural, conductive, and thermal management all in one.
It's pulling triple duty. And looking ahead, that positions it as the essential, sustainable chase for the next generation of large-scale energy storage.
Before we wrap up, the sources clarify two terms that often get confused: power and energy. Let's quickly touch on that.
It's a really crucial distinction. Energy is the total capacity to do work. So it's the total amount of electricity generated or stored over time. We measure it in kilowatt hours.
Okay, so energy is the total volume. Then what is power?
Power is the rate. It's how quickly that energy can be supplied at any given moment. We measure that in kilowatts or kilowatt-hour.
So aluminum helps with both, right? Its structure helps maximize the energy that can be generated or stored, the kilowatt-hour.
While its conductivity ensures the power, the kilowatt-hour can be transmitted quickly and reliably.
That's a helpful clarification. Now, we've focused on the good stuff, but our sources remind us that every system has trade-offs. Let's briefly review the pros and cons of solar energy.
Of course. The benefits are immense. It's clean, renewable, and as we've said, it's compatible with these lightweight profiles, which makes assembly easier.
Plus energy independence, cost savings over time.
But the drawbacks are real. The main one is dependency on weather and location.
Intermittency.
Exactly. Output is inconsistent. Then you have the high initial investment costs, though they are coming down.
And the two biggest challenges seem to be the ones we've just discussed.
Right. The storage problem, which requires these robust, thermally managed batteries, and then the substantial space requirements for large farms.
Okay, so to synthesize this whole discussion,
Aluminum isn't just a nice-to-have material here. It's indispensable. It simultaneously delivers lightweight strength, high conductivity, and exceptional sustainability through recycling.
It provides resilience across generation, transmission, and storage.
Every single stage of the modern grid.
So what does this all mean for you? The next time you see a solar panel on a roof or a new high-voltage power line, just recognize that the material making it all physically possible isn't some exotic composite.
It's reliable, constantly being customized aluminium.
It's the literal scaffolding for a greener future.
And here's a final thought for you to mull over. Given that astounding fact that recycling aluminium takes only 5% of the energy of making it new, consider the long-term compounding effect of that. As we build out all this renewable infrastructure today, we are not just creating energy capacity. We're also stockpiling a high-value, fully recyclable commodity that will pave the way for a truly resilient circular energy economy decades from now, when all of this eventually needs to be updated.